the organized Southeast Show, and also like one for organizing, they great efforts in organizing this conference, so that we have opportunity to university. Okay, the lecture, the second one is Professor Stefan Antusch of the University of Passau, Switzerland. He got his PhD in 2003 from Technical University of Munich. And then he has some research experience at the University of Southampton, also University of Israel, and then also Max Planck. And then he finally in 2011 joined his university. Okay. And he has a mentor or supervisor 5 postdoc research, 6 PhD students, and 3 diploma students. Master student. Okay, so he's going to give a lecture on the neutrinos and physics beyond the standard model. So let's welcome Professor Stefan Antusch.
Yes, hello, thank you very much. It's a great pleasure to be here and give these lectures on neutrinos, physics beyond the standard model. So before we start, 2 things. So the first thing, I'm going to mix up my lectures with some slides and also something written on this whiteboard here. So please check now if you can see everything on this projector here. So I'm especially new here at this point. If you don't see, I would recommend moving a bit more to the middle, then you have a better view. But if it's okay, then of course stay where you are. And then the second thing is when you have any questions during my talk. So you can always interrupt me and ask the question if something is unclear. I can explain this in a bit more detail. So don't worry and just interrupt me for any questions. Okay, so let's get started. First thing, a little bit about myself. I'm a theoretical physicist and I'm working on physics beyond the standard model. So the goal here is to arrive at a more fundamental theory than our current standard model of elementary particles. Especially with my group, we are attacking this from different sides. So one side is from neutrino physics. So we know that neutrino masses, in order to include them, we have to go beyond standard model. Especially in this first lecture. Also, another direction is to come from the quest for a unified theory, or a more fundamental description where you can unify the 3 forces of the standard model into one unified force, and also to explain the origin of flavors. There's a motivation to arrive at a more fundamental theory, maybe. So that's another direction where we attack this beyond the standard model of physics stress. And the third one is coming from cosmology. So if you want to explain consistent evolution of the universe, the flatness and the homogeneity of the universe today, also dark matter and so on. These are all questions which you also want to solve if you want to arrive at a more fundamental theory. So the goal is to be at some point here in the middle where we can solve all these challenges simultaneously. And especially in these lectures here, I would like to cover neutrino physics, connection to the standard model physics, and also how this is connected to unified theories and the topic of flavor. So how can the flavor structure that we have in the report and in the lecture section be explained by extension of the standard model. So the lectures are going to be organized as follows. So we will have 3 lectures. So the first one will be on the basic neutrino mass mechanisms and also on implications of them, how we can eventually test them with experiments. The second one will be the connection between neutrinos and grand unified theories. And the third one will be the connection of neutrinos and flavor models. Okay, so let's get started with the first lecture, which is on the basic neutrino mass mechanisms. And of course, I would like to start at the present status. And the present status is the standard model elementary particles. So I guess everyone of you is familiar with it, and one can find it even on coffee pots. So admittedly in a somewhat condensed notation, but you can really formulated in a very short way that it even fits in here. But of course, if I want to explain that we have to go beyond the Standard Model, I should expand a bit more than just showing this coffee pot. So, okay, what is the Standard Model actually about? So the Standard Model is based on gauge symmetry, so it's a quantum field theory in the first place, and it's based on local symmetries, namely SU3 times SU2 times U1, where the SU3 here is the interaction of the QCD, where the electric fields are the gluons. We have here the SU2 cross U1, so this is actually a unification of the weak the electromagnetic interactions, the so-called electroweak interactions. And then this gets broken by the vacuum expectation value of the Higgs field to the QCD and the electromagnetic interactions. So in the Standard Model, one can say that we already have some unification of forces, the unification of the electromagnetic and the weak interactions, the electroweak interactions. But we have not yet unified here with this third force. Okay, so when you look at the Lagrangian of the Standard Model, so there are different parts, different pieces. So the first one is the one connected to this gauge field, so to this vector field here, which mediates the forces. Okay, so this here is with F being the field strength. This is a term here in the Lagrangian for a pure gauge theory, and you can have here all the gauge fields written as these fields here are the generators, so you can construct the field strength with this here, or in this form is the covariant derivatives with a capital D here, and then you have the theory for pure gauge. Okay, then the next part in the Standard Model Lagrangian is the part with the Higgs field. So we have here the kinetic terms with the covariant derivatives. This also contains the interaction of the Higgs field with the gauge bosons. And we have here a potential for the Higgs field. And if this mass term here, the interior, is negative, then actually the Higgs field being at zero is not stable. So we have a potential of this Mexican head shape here. So this here would be phi equals zero, it's not stable. And we have spontaneous symmetry breaking. The field would choose some vacuum expectation value. For instance, by convention, one could take it in this direction. And then this electroweak symmetry gets broken, or here to the U1 which remains. This remaining symmetry is the one of electromagnetism. So that's the Higgs mechanism. The Higgs has been discovered, and this is another part of the Standard Model that we know in the meantime much better since the discovery of the Higgs boson. Furthermore, the Standard Model is defined by its meta content. So we have already seen the gauge field, we have the Higgs field, but there are also fermions in the Standard Model which make up the matter, and the Higgs together with the fermions can be put here in this table, which gives the field content of the Standard Model. So we have here the quantum numbers or the representations under the SU3 color, under the SU2, and under the U1. So this here is the quark doublet. So it contains the up and the down quarks, the left color up and down quarks. It's a triplet under the SU3 color, a doublet under the SU2 left, and it has 1/6 of the weak hypercharge. Furthermore, we have here the lepton doublet, which of course doesn't have to be colored. So these are leptons. It's again a doublet on the SU2 left. It is -1/2 units of weak hypercharge. So these here are the only fields which are non-trivial representations here. The only fermions and non-trivial representations of the SU2 left. The other field in non-trivial representation is the Higgs field here. It's again, doesn't have any color, but it's a doublet under the SU2 left, and it has +1/2 weak hypercharge. And if you know the weak hypercharge and the isospin that will be +1/2 and -1/2, if it's in an upper or lower part of this of such an SU2 doublet here, then you can calculate also the electric charge of it after spontaneous electroweak symmetry. So in addition to these ones which are in the SU2 left doublets, you also have SU2 left singlets, so kind of right chiral fields, which I write here in charge conjugate form, so should they also left chiral, so everything is expressed in the same fundamental representations of cell C. And these are then kind of the right-handed quarks, up quarks, the right chiral down quarks, and the right chiral charge levels. This index here, I, goes from 1 to 3 for all the 3 families that we know of matter. So this is kind of the symmetries together with this table here, the parameters of the Higgs potential. These are basically everything you need in order to write down standard model terms in the Lagrangian, but there's nothing missing, which are the Yukawa couples which then in the end give masses to the fermions. So with this field content, you can write down the following additional part of the standard model Lagrangian, which is this here, which is basically the terms for the fermions here in the theory. So first of all, we have here the kinetic terms, which contain the covariant derivatives, and these here give the couplings of the fermions to the corresponding Dave bosons, depending on the charge that these fields have. So this is hidden here in this covariant derivatives. And then there are more terms, like these ones here, which couple the fermions to the Higgs field. And you can couple here either to phi, or to the phi tilde, which is epsilon tensor times phi complex conjugated. And these terms here can, after spontaneous symmetry gradient, lead to masses of the fermions. Okay, now you can think, okay, which of these terms can I construct here? If I go back and look at my table, so you know which are the representations. The condition is that these terms here in the Lagrangian all have to be singlets under all symmetries. So you can only write them in the Lagrangian if these complete terms here are neutral under the group transformations. And then you see what you get is you get masses for the uptime quarks, the downtime quarks, for the charged leptons, but you cannot write down any mass term here for the neutrinos. So only a charge field get masses, but the neutrinos do not get any masses. So you can easily check what you will need for a mass term for neutrinos. So if this phi has its left in the well, let's look here. You would like to connect the left-handed doublets to the Higgs field here. Okay. And then what is this here are two doublets, which you can contract to a singlet. These hypercharge would add up to 0. So what is missing here is a field here in the representation, which is singlet under SU3 color, singlet under SU2 left, and singlet under the deep hypercharge. So what is missing is kind of a right chiral counterpart of the left chiral neutrinos. If you would have this, then you could write down the mass term for the neutrinos. But this one would be one specific extension, which we will recover already then also a little bit later. But in any case, with this field here, which define a standard model, you don't have any possibility to construct such a mass term for the neutrinos. So nothing like this here exists in the standard model for the neutrinos. So no renormalizable mass term. However, there is a possibility to introduce neutrino masses without going to extra new fields or introducing new fields to the standard model. And this is by realizing that the standard model is most probably not a full theory, or we know it is not a full theory, it is just an effective theory. So this means that this is a theory valid at the mass scales which we can test it at the moment at colliders up to some energy scale. But then above this energy scale, it should be replaced by a more complete theory. So if you have this picture of an effective theory, then you should introduce effective operators which parameterize this ignorance that you don't know the full theory above the scale. And for such an effective operator, you can explain quantum neutrino masses. This is not a long time ago, 1979. Steve Weinberg has introduced such an operator. And this is a thing I would like to go through here on the blackboard, naming neutrino masses in the effective standard model. that the standard model is indeed an effective theory, then you can generate neutrino masses by an effective dimension 5. Okay, how does this operator look like? So we have here some dimensionless coefficient, or sorry, some coefficient which has dimension 1 over mass. We need our two neutrinos, our two standard model neutrinos, so we need two doublets. And we have to couple these doublets to the Higgs fields. So if you write down an operator like this here, plus emission conjugate, where this dot here stands for the SU2 product. So it's basically if this small A, B, C are indices of the SU2 representation, they go from 1 to 2, and we have an epsilon tensor, totally antisymmetric 2 over 2 matrix. So that's an invariant product of two SU2 doublets. And with this, we have here an operator which is first of all neutral under the SU2. So we have contracted these doublets here to singlets here and there. We are also neutral under big hypercharge because we have +1/2, -1/2 for the Higgs doublet and for the lepton doublet. And so this is an operator which is allowed by the standard model symmetries, but we are normally just not writing it down because it's non-normalizable, or it's an effective operator in a sense. So which means the theory makes sense up to this, up to a certain scale. So this couple here is a parameter which is proportional to 1 over some mass scale. And this is the scale where we have to introduce new physics. So above the scale, the standard model is not a good theory anymore. And one can also think of this operator here diagrammatically, then it's also more clear what it's doing. We have two doublets, Li, Lj. So, right, we get the complex conjugate of this operator. Same as ingoing fields. Higgs field. And when this thing gets a Bachmann expectation value, it basically projects out here the left chiral neutrinos. And what you're ending up with is electroweak symmetry breaking. You're generating a master of the neutrinos this form. Where this mass matrix here is connected to this kappa coefficient matrix. Okay. So it is proportional to the electroweak wave squared here. So this crosses here corresponds to the search of electroweak vacuum scale, and then divided by this lambda here by this scale new physics. So this here is a way to write down neutrino masses without explicitly extending the standard model. So does this mean that, okay, neutrino masses are not really just part of the standard model? Well, no, because as we said here, so this here is just an effective description, but it's not a fundamentally valid theory. So at some point, or more specifically at this scale lambda here, we have to write down a new theory. So in some sense, we have to replace this effective operator here by some famous diagram with some explicitly introduced new particles that are interchanged. And what exactly these extensions are, this is what we will discuss a bit later in this lecture. So the next thing I would like to discuss with you is what we know about the parameters of the standard model fermions. So we have, on the one hand, we have the masses, so that we already discussed. We had this term, the standard model Lagrangian, when the Higgs gets its vacuum expectation, then we generate the masses of the fermions. But we also have mixing. Okay, so how is this mixing defined? So well, here again are now a bit more explicitly what we have in the quark sector for these couplings of the fermions to the Higgs fields. So we have here this coupling of the quark doublet to the right up quarks and the phi tilde. So this here projects out the up quarks. And if you multiply this Yukawa matrix times the electroweak vacuum scale, then you get the masses, or the mass matrix of these fields. Okay, and this here is the corresponding term in the down sector. So we have here the quark doublet times the Higgs doublet times the right down field, and this matrix here times the electroweak VEF gives the mass matrix of the down fields. Okay, now we can diagonalize the mass matrices for respectively the Yukawa matrices by Y-unitary transformations. So like this is done here. And then these eigenvalues here, these are the masses of the mass eigenstate field. So the mass eigenstate up quark, down quark, top quark. And the same also is here for the down sector. So we have left carbon transformations. Right, so we have a left unitary transformation for the left cover field, the right transformation for the right cover fields, and with this we can also diagonalize the mass matrix for the down quark, and the eigenvalues here are the mass of the down quark, the strange quark, and of the bottom quark. And now the quark mixing matrix, so the CKM matrix, is defined of the product of the left diagonalization matrix for the up quarks times the daggered, so complex conjugate and transposed diagonalization matrix, left diagonalization matrix for the down quarks. And now the pairs of fields that participate in the weak interactions, so you can only choose one of them as the mass eigenstate, and the other one is rotated by this CKM matrix. So you can now here remove the unphysical phases such that you arrive at this parametrization here, which only has the physical degrees of freedom, and you can parameterize this as a 2-3 rotation, which is real, a complex 1-3 rotation, and a real 1-2 rotation. So this, I think, you're all familiar with. And this is the 3 mixing angles in the quark sector, and the one so-called Dirac phase in the quark sector. Okay, now that neutrinos have masses, we have something analogous also in the lepton sector. And if you want to write this in a very minimal way, we can say we just introduce neutrino masses in the effective standard model, as we've done this here, via such an operator. So we could add to the standard model just this operator, then we have the mass matrix for the neutrinos, given by this term here, in the Lagrangian. And we have in addition a similar term that we discussed before for the quarks. Here's the analogous term for the charged leptons. So it has the charged lepton Yukawa matrix, and here we have the lepton doublet, Higgs, and the right cover electrons. And now if here the Higgs field gets its vacuum expectation, then it will give a mass matrix for the charged leptons, which is this here, times selectively BEV. So this here is the mass matrix. And then we have diagonalized it again with left and right rotations. So furthermore, you can also diagonalize the mass matrix here for the neutrinos. This will, you only need one left unitary matrix, and you diagonalize it U times matrix times unitary matrix transpose, which is actually what matches this structure here. So you have this this kappa operator matrix in between the transposed field here and the normal untransposed field here. So by transforming the fields, you can diagonalize this matrix, and you have three eigenvalues, M1, M2, and M3 for the neutrinos. Okay, now we have, again, a mixing matrix which appears in the charged current interaction with the W bosons, which is the so-called PMNS matrix, which is the left charged lepton matrix times the left unitary diagonalization matrix for the charged leptons times the unitary diagonalization matrix of the neutrinos dagger. And again, you can remove unphysical phases, and you can bring it to this form here, depending whether the neutrino masses are of Majorana type or not. You may have two additional phases, but the first part here is the same as we had for the CKM matrix. 2-3 mixing matrix, 1-3 complex rotation, which has the Dirac P phase in it, and this here is the 1-2 rotation in the so this is kind of, we have 3 mixing angles as in the quark sector, and one of them is complex, which is the Dirac phase. And what exactly Majorana and Dirac masses are, we'll explain in detail in a few transparencies. Okay, so the next thing I would like to review with you is the present status, what we know about all these parameters that I've just introduced, masses and mixing angles. So starting with the masses. So we know that we have here very hierarchical masses in the quark sector. So here are the masses for the up sector, for the down sector. What I'm presenting here, these are all running masses at C mass in order to have them comparable. So this will not be the things which you find in the particle data group. Normally they are partly different energy scales or whole masses. These are masses have to do the renormalization to come into a common scale. And you see that, well, there's a very strong hierarchy. The hierarchy is even stronger here in the up quark sector than here in the down quark sector. So if you compare the top mass here is by far the most heavy, so the bottom mass here is much smaller, whereas the first generation here is roughly comparable. So there's a much stronger hierarchy in the up sector still than in the down sector. Whereas on the other hand, charged lepton masses, if you look at them here, they are also very hierarchical, and I think very similar actually to the masses that you have here in the down quark sector. The charged leptons in the down quark sector, apart from some factors, but they're in between where they have a quite similar mass hierarchy. So that's only one question, which I will come to in the third lecture. So how can we actually understand why these masses are so much hierarchical? It's also possible already in the standard model that there are so different masses measured for the 3 generations of fermions, of the charged fermions. Okay, for the neutrino masses, the situation is that we have only measured so far so-called differences of squared masses. So not the mass scale themselves for neutrino oscillations, the only thing we have are differences of squared masses. This is the M3 squared minus M1 squared. Here we don't even know which of them is lighter, M3 or M1. But the modulus of this is 2.7 times 10 to minus 3 electron volts roughly. And M2 squared minus M1 squared is about 7.5 times 10 to minus 5 electron volts squared. And for the absolute neutrino mass scale, I think we have just rough bounds that it's below something like 1.5